Okay, for this section we're going to be focusing on the difference between gravitational versus electric potential energy. So it can take work to move a charged object from place to place in an electric field. This work changes the energy of the charge, just like lifting an object in a gravitational field changes the energy of the mass. Just to remember, when you apply a force over a distance, you change the amount of energy the object has. And that says that you're basically doing work on the object. So let's take a look at gravitational potential energy. If I've got these two positions here, and I've got this little cliff, and at the bottom of the cliff I'm going to call this position A, and at the top of the cliff I'm going to call that position B. So if I put a little mass right here at the bottom of it, and I pull it up to the top of the cliff, as it's being pulled up against against gravity, or the gravitational field, I'm doing work on it. I'm applying a force over a distance, and that's changing the amount of energy it has. Specifically, the amount of gravitational potential energy, which is mgh. So by moving it up to a greater height, I'm increasing the amount of potential energy it has. So if the mass is moved from point A to B, there is an increase in the potential energy of the mass. However, if I had it at B and I was just to let go of it, then it's the force of gravity that's doing the work and pulling it down. And that would cause a decrease in the potential energy of the mass. Let's compare that to electric potential energy. So let's say if we've got this little circle here, I'm going to make it positively charged. So we're going to make it negatively charged. And right at the surface of it, I'm going to call this position A. I'm going to put a little positive charge. Now, just like the mass was attracted to the ground, this positive charge would be attracted to the negative charge. If I was to pull this away, I would be doing work against the electrostatic force, working against it. And by pulling it away, I'm actually giving it more potential energy. Think of it almost like a spring. If you stretch the spring, it wants to compress, so you're giving it more stored energy. However, if you have it at position B, and you let go of it, it's going to snap back. So it's going to take that stored energy it has at position B and convert it to kinetic energy, and therefore decreasing the amount of potential energy as it goes from B to A. Now we have to look at this in two different scenarios. One, when the two charges are being attracted to each other, they're opposites, and then also when they're like charges. So let's look at the same type of scenario, but I'm going to now make the source charge positive. And I'm going to have a little positive charge here at the surface of it. Now in this case, they're being repelled away from each other. So if I was to move it to position B, well, it would just want to repel on its own. I wouldn't actually have to do physical work in pulling it away from it. It would just kind of blast itself apart. So in this case, as it goes from A to B, there would be a decrease in the potential energy it has. Vice versa, if we go from B to A, well now this positive would be wanting to repel away from the positive, so I've got to push it and force it back closer to it, and therefore increasing the amount of potential energy it has. So in general, anytime a charge is moved up or down in an electric field, there's going to be a change in the electric potential energy the object has. And it has to be moving up and down. If I was to move it, like in those two different scenarios there, to the left or the right, I'm not changing its position or distance it away from the source charge, so it's not going to change the amount of potential energy it has. Just like if I was to move an object to the left or right above the surface of Earth, I'm not changing its height, and therefore I'm not changing its gravitation potential energy it has. Now, if the direction of the electric field is such that it opposes the motion of a charged particle, work must be done to move the particle in that direction, as we just shown in the previous slide. The work done per unit charge in moving a charge between the 2 points in an electric field is known as the electric potential difference. Let's look at it in this case here. Let's say we have this negative charge, center. I'm going to call this position A and this position B. I'm going to put a little positive charge right here. Now, if I was to pull this away, applying a force over some distance, work is being done on the charge against the field. The electric field would be pointing inward, the negative charge. So now that it's up here at this position, we could say, and keeping this still negative, we could say that it went from a low amount of potential energy, or we would just use potential, just the ratio between the amount of energy it has per unit of charge, to a high potential. On the other hand, if it's far away from the positive charge, the positive charge is far away from the negative one. So now, work is being done in the same direction of the field. Field. So it would go from a high potential, have a lot of energy up here, stored potential energy, to a lower potential. Now, our equation for potential difference, a simple little bit, is capital V, and that's equal to W divided by Q. Where the W represents work or electrical energy, and the Q is the charge that's being moved. Having the work done on. Now our units for this, well, if we go to our equation, work, or electrical energy, is measured in joules. And charge is measured in coulombs. So we could call this joule per coulomb. Well, if it's joule per coulomb, we have an abbreviated unit for it, and we call it a volt. The symbol for it is capital V. Let's look at these examples. Moving a point charge of 3.2 times 10 to the negative 19 coulombs between points A and B in an electric field requires 4.8 times 10 to the negative 18 joules of energy. What's the potential difference between the 2 points? So, we know the amount of charge that's being moved, 3.2 times 10 to the negative 19 coulombs, and we know the amount of work it takes to move it. 4.8 times 10 to the negative 18 joules. We want to figure out what the potential difference was. So our equation is just W divided by Q, where W is 4.8 times 10 to the negative 18 joules, and Q is 3.2 times 10 to the negative 19 coulombs. Do the math there, it just turns out to be 15 volts. Look at the next one. How much electrical energy is required to move a 6 microcoulomb charge through a potential difference of 36 volts? So we know the charge here is 6 microcoulombs. Now we've got to get rid of that micro because we just want to have it as coulombs there. A micro is a millionth, or 6 times 10 to the negative 6 coulombs. We know the potential difference is 36 volts. What we're looking for is the amount of electrical energy, and that's the symbol capital W. So our equation is V is equal to W over Q. Manipulating this around, V times Q. So we take the potential difference, which is 36 volts, multiplied by the charge, which is 6 times 10 to the negative 6 coulombs. We'll work out the math there. Turns out to be 2.16 times 10 to the negative 4 joules. So that's how much energy it would take to move that amount of charge through the potential difference is 36 volts. Look at this last one. Determine how many electrons are moved if it takes 1.5 times 10 to the negative 5 joules of energy to move them through a potential difference of 15 volts. So this one's got kind of two steps. First, we want to figure out the potential difference is 15 volts. And the amount of energy it takes to move those is 1.5 times 10 to the negative 5 joules. There's going to be two steps involved in this problem. First, we want to find the amount of charge that was moved. I'm sorry. First, we're going to need to, if we want to find the number of electrons, we'll first need to find the amount of charge that's moved and then convert that charge to electrons. So we can do that by using our equation V is equal to W over Q. Solving for Q, W divided by V, we're going to do 1.5 times 10 to the negative 5 joules divided by V, which is 15 volts. So the amount of charge that was moved turns out to be 1.6, 1 times 10 to the negative 6 coulombs. Now we know the amount of charge that's being moved. We can take that amount of charge and convert it to just elementary particles, or electrons in this case, using a ratio that one elementary particle is going to carry 1.6 times 10 to the negative 19 coulombs. So, start with our given, 1 times 10 to the negative 6 coulombs, multiply by a fraction. We're going to put 1.6 times 10 to the negative 19 coulombs down below, and the charge of that, well, that charge represents one elementary particle, and that will be 6.25 times 10 to the 12th. Electrons.